Good evening, students. This is your section 1.7 video. It's about absolute value applications. Let's dive right in. I'm going to try to be more humorous this video because I think you want that. Let's go. Essential question. How can I model tolerances with absolute value equations? Now, we need to define the word tolerances. I will get to that in just a second. Let's look at our first example. Example 1. Baseballs are designed to weigh 5.125 ounces with a tolerance of 0.125 ounces. I want to write an absolute value equation to model this situation. So I need to define the word tolerance for you still. Before I do that, maybe you don't know what a baseball is. Here's an excellent picture of a real-life baseball game that took place in Muppet Land. Here you see Kermit the Frog is holding a baseball, and what is this guy's name? Beast, monster, animal. He's going to try to hit the baseball. So back to the example. Baseballs are designed to have this kind of ideal weight of 5.125 ounces. So if I'm a manufacturing company, I'm trying to make the baseball weigh exactly 5.125. However, as I learned in my glory days as a 1.5-year engineering student before I switched over to math, there are these things called tolerances because in the real world, machines are not perfect. They're not going to be able to make the baseball this weight every single time. And so in order to not throw out every single baseball that's made that's not exactly that weight, manufacturers say, hey, listen, we're going to try to make it that weight, but if you are 0.125 to this side or 0.125 to this side, you're good to go. In other words, if you're a little bit off, but not too much off, we're going to accept that baseball. So let's think about what that means in this context. 0.125 above 5.125 would mean add them, right? And that's 5.25. 0.125 on the lower end of 5.125 would mean subtract them, and that would just be 5. So as long as my baseball is somewhere in between 5 and 5.25, I have a baseball that's going to be acceptable. If it's outside that range, the baseball's no good. Or the other way to think about it, the way we're going to need to think about it when we set up our equation is I need the distance between this ideal weight and my outside bounds to be less than 0.125. As long as I don't go 0.125 away from my ideal weight, I'm good to go. So let's use that knowledge of distance in order to set up our equation. Let's say my baseball weighs X. So I just produced a baseball. I don't know how much it weighs yet. It's X. I need the distance between this baseball and the ideal baseball to be less than or equal to 0.125. So notice what I did there. I have a baseball. I don't know how much it weighs, but I know that if I subtract that weight from the ideal weight, it's going to be a certain distance, right? So let's say my baseball weighs 6. Let's see how far away 6 is from the ideal weight. So if I subtract them, I would get 0.875, and that is clearly way bigger than the tolerance. So I need the tolerance to be less than or equal to 0.125. Distance is measured with subtraction, less than or equal to the tolerance. Now I need to do just one more thing before I finish off my equation. Remember how this is the absolute value chapter? Here's the thing. Since I could have my baseball being above the ideal weight or below the ideal weight, I need to take that into account by using absolute values. Here's why. Let's say that my weight of the baseball is below 5.125. Let's say it's like 5.1. So when I'm subtracting, aren't I going to get negative 0.025? But I don't really care about this negative. I just care about the 0.025 part. And I care about the fact that that 0.025 is indeed less than the tolerance. So this would be a good baseball. Since I don't care about the negative part, since I'm only caring about like the absolute difference, that's why I choose to use absolute value bars, because they take off the negative. They refer only to kind of the absolute difference. So I'm going to use absolute values for all of these equations because I don't care if my baseball is below or above. I'm just caring about the absolute difference. Now, this problem might seem a little bit tricky to you. Just know that in any case, you can use this same general format of x minus the ideal in absolute values, because I don't care if it's below the ideal or above the ideal, and that always is going to need to be less than or equal to the tolerance. So if you remember this kind of specific format, you'll be able to solve all the problems in this section. Let's look at one more example so that we can try to put this into practice. This one says, example 2, a certain brand of backpack is recommended for loads ranging between 22 and 29 pounds. And I need to, again, write an absolute value inequality for this weight range. So let's just make sure you know what a backpack is. Here's your highly attractive teacher wearing a highly attractive purple backpack in the highly attractive land of Capri, Italy. See that island? Pretty sweet, right? Another thing that's sweet about this picture is my hair. Just take it all in. It is way back. My widow's peak is revealed. I almost kind of look like Wolverine here. Good stuff. Back to the math. Backpack. I need it to be between 22 and 29 pounds. So the manufacturers are saying, hey, as long as you're within this range, that's where you want to be using our backpack. If you go outside of this range, don't do it. You're using another backpack. Now keep in mind, I need to be fitting into this kind of absolute value x minus ideal less than or equal to the tolerance, but they haven't given me the ideal or the tolerance in this case. They've just given me the boundaries, 22 and 29. So I need to find what the kind of ideal weight they're looking for is, and then from there I can find the tolerance. So let's find the ideal weight first. In other words, what is the weight that is right in the middle? What would be literally the perfect weight to use this backpack with? Now, there are a couple different ways of finding a value in the middle. You might be able to just look at 22 and 29 and figure it out. You can also always take their average. So let's average 22 and 29, which means add them up, divide by 2. That would be 51 over 2, so it comes out as 25.5. So my ideal weight here is 25.5. That's the weight right in the middle, and let me replace ideal with 25.5 in my formula. That's the weight I'm shooting for. Remember, the tolerance is the distance away from the ideal weight that I am allowed to go. So in this case, what is the distance between 22 and 25.5? What is the distance between 25.5 and 29? And you can just easily do that with subtraction. 22 and 25.5, they are separated by a distance of 3.5. And then also 25.5 and 29 are separated by a distance of 3.5. So away from the ideal weight, I'm allowed to go a tolerance of 3.5. As long as I don't go away from the ideal weight by more than that, I'm good to go. And so this is my final equation. All right, so your summary, keep in mind, it's word problems, it's a little bit tricky, but to model tolerances, you can always use the following format. Absolute value x minus ideal is less than or equal to the tolerance. Remember, I'm using minus because I need to make sure my value is less than the ideal. It's a certain distance away from the ideal by less than the tolerance, which is how far away from the ideal weight I'm allowed to go. And I use absolute values because it doesn't matter if it is on the positive side or the negative side. Either way, I need it to be less than the tolerance. So good luck with the problems in this section. They're tricky. Use that format and you'll be good to go.